All right, so we're going to catch up on. We're going to eventually get to talking about large waves and what they have to do with El Nino, and also there's something else called the Bjerknes feedback. That's very important. Bjerknes is a person. A feedback is a thing. So we'll explain that bit of the story, and it also brings back some of the other themes of things we've talked about so far, like upwelling. All this gets linked together when we think about the pieces that are necessary for El Nino. But before we get there, I realized that I skimmed a bit quickly over the Rossby waves. So we'll look through a little bit of the Rossby waves because we need a few more pieces to make sure we've really got it clear before we get to their impact on El Nino. I think the Kelvin wave part, we did a lot of discussion because it has the tidal piece, but the Rossby waves were kind of tacked on in the end. So let's start there, and then we'll come back. So, did I just open the wrong slideshow? No, that's just from yesterday. Sorry, that's the wrong one. Is it? Oh, yeah. All right, here we go. So, we're now starting to get familiar with these ideas of group velocity and phase, speed, and dispersive and non-dispersive waves, wavelengths, frequencies, angular frequencies, wave numbers. So hopefully some of these concepts are drifting in. These will be useful whenever you're doing any kind of waves, but we've actually started talking about a lot of different kinds. So now our table of dispersion relations has actually started to fill in pretty nicely. We have the non-dispersive plane waves with a constant phase speed. We have surface gravity waves, which have this GK tanh KH thing, of which, if you go to the limit of short waves or deep water, it's omega squared equals GK. If you go to long waves or shallow water, then it's omega squared equals K squared GH. So since if GH is constant, then we see it's a non-dispersive plane wave with a constant speed. And then we touched on internal waves, and I did not derive the dispersion relation for internal waves, but I think it is actually derived in Wunsch's book. And I think I did derive it in the slides that I skipped over. So if you're interested in talking about internal waves for your fourth paper, that's kind of an interesting thing to do. They are really crazy in that their dispersion relation depends on the buoyancy frequency and the angle from the vertical, but nothing else. And so like Rossby waves, they have a really weird phase velocity, group velocity relationship. So if this is the direction of internal wave propagation in terms of the group velocity, the phase goes this way. So the phase speed is always perpendicular to the group velocity, which is seriously weird. So anyway.
Can you say that one more time?
Yeah.
Slower?
Okay. So suppose I'm in the uniformly stratified water, and I start making waves by wiggling down here. They will propagate energy away from the source, but the weird thing is that the phase of those waves, the crest and troughs, they propagate perpendicularly to the direction of the energy propagation. So as the energy is going away from the source, you see it in beams that are moving like this. So once again, do not confuse waves. Dispersive waves are weird. It is not necessarily the motion of the water that transports the energy. It is a communication of information from one place to another that can transport energy, and there are crests and troughs involved, but the crests and troughs might be doing something very seemingly independent of the propagation of the energy. So it's, once again, so when you learn this and you do light, and light always has the same speed and everything is simple and easy, you think waves, I totally understand that, that's not so bad. When you get into some of the more obscure examples, things start to get a little hairy. Okay, and then the one case we did talk a little bit about is if you have internal waves that are on an interface, say on the picnic line, and then you just get a G prime instead of a G for waves that are propagating on that interface. So if G prime is the fraction of the density, so density in the upper layer, or density in the lower layer minus density in the upper layer divided by their average, how fast do you expect the internal waves to be compared to the surface waves? Maybe I'll write it out while you're thinking. Except I can't because somebody has stolen all the markers and moved them to the opposite end of the room. So first, what's the group velocity for? So if omega squared equals k squared g prime h, what's the speed or the velocity? Square root of g prime h would be c, which is also cg. So if g prime is rho 2 minus rho 1 over the background rho times g, is that going to be bigger or smaller than g? Smaller, because these are going to be close. So maybe upper ocean water to lower, this might be 2% of g. So, well, I can't take the square root of 2%. Square root of 1% is a tenth. So it would be 10 times slower than a surface wave. So the internal waves are going to have frequencies that are order 100 times lower, speeds that are order 10 times lower. It's a different part of space. So it's just useful to have that. The internal waves are going to be different than the surface waves because the density difference between layers in the ocean is not as big as the density difference between the ocean and the atmosphere. So where surface waves are fast, internal waves will be slower. Where surface waves propagate fast, internal waves will propagate slower. And then there's also this crazy thing when there are internal waves that aren't just on a single interface, but in a uniformly stratified fluid. It's a more complicated situation. But I just wanted to give you some sense of that part of the story if you're interested. Okay, so we did talk a lot about Kelvin waves last time. And which way do they propagate?
The shore is on the right.
So the shore is on the right in the northern hemisphere, or the shore is on the left in the southern hemisphere. And we're going to get to a different kind today, which is with the equator, propagating along the equator from west to east. So that's an equatorial Kelvin wave. And then here's the Rossby wave dispersion relation, which we didn't really discuss much, except to say that the deformation radius was involved, and it's super complicated, and it's a single power of omega. So what does that mean about the direction of propagation?
Unidirectional.
It's unidirectional. So I'm going to return to that in a minute. Okay, so here's our blob drop, and we saw the Kelvin waves run off. So it's northern hemisphere, and then this is a side view, and those marks mark the initial location. So the blob is slowly drifting west. So the first blobs run away was the Kelvin wave part, and this slower bit is the Rossby wave part. And in order to have a Rossby wave, so the Rossby wave dispersion relation depended on beta, which remember is the change in F from south to north. So you don't get Rossby waves if you have a constant rotation rate. So you have to have a beta. So this is actually on a beta plane. So this end, if you like, is more north than this end. So I have a little bit larger F up here than I do at the bottom, just a tiny amount. And so the wave drifts to the west based on that north and south. Yeah?
Are Kelvin and Rossby waves considered surface waves?
Sort of, yes. In this case, we're just doing a shallow water equation, so a single layer that's moving. And so in that sense, they have a surface expression in terms of high and low pressures. And so yes, but we could have done this in a reduced gravity and just had the upper layer moving. So then the anomaly is in that interface between the layers more than it's at the surface. And so they are a thickness anomaly wave, but you might not necessarily call them a surface wave in the same way that we call surface gravity waves surface waves. They are absolutely at the surface, and if you rewind back to our Poisson equation and all that, it was actually a boundary condition in the surface boundary condition that allowed them to exist. These waves are not coming from a surface boundary condition in the same way. They're an anomaly in the thickness of the whole layer or the vorticity of, and that deviation from a latitude picture that we showed last time. I'll come back to that and talk about that again. So they're not quite a surface wave. They could have no surface expression at all and still be a Rossby wave or a Kelvin wave. Is maybe a better way to put it, even though sometimes they do have a surface expression. Okay, so we jumped through the equations last time, but I actually thought it might be a little bit helpful to walk through them for a Rossby wave. So we're on a beta plane, which means that F has some meridional variation, which is set by beta. And so in our little channel, F would be a little bit bigger at the north end of the channel than it was at the south end. This is a small number. So this is 10 to the minus 4 per second. This is 10 to the minus 12, typically, per second per meter. So you need something like 10 to the 7 meters, which is 1,000 kilometers, for this to be as big as that. So for most, kind of planetary scale features, this number is going to be a lot smaller than this number, even the limits of this number from the top to the bottom of the region you're thinking about. Okay? So if that's true, if beta times the length scale of your motion over F naught is much less than 1, we can simplify our shallow water equations of motion. So here's our time tendency, and we would have advection, u dot grad, but we don't have advection. Why not?
It's not significant.
Because we're going to pretend it's not significant, even though, remember at the end we said maybe that Chilton and Slack story, maybe they're not really waves, maybe they are eddies. We threw away the part that would make them eddies. We're making them waves. It's not really justified. They might actually be eddies, but we're just going to pretend that the one particular one we're thinking of is not very strong. So the Rossby number stays small and we throw it away. Okay? But that's not true in the real world. That is true of this derivation, that we've decided to take a small amplitude signal in order to keep it linear. Here's the Coriolis term. So F naught, U and B are scrambled with these with the minus sign. So that's F cross the horizontal velocity written out in components. We have F naught plus beta Y, so we have both bits. And then here's the sea surface height part, giving us a pressure gradient force, just like you've been doing for paper 3 on the gyre. And then we have a thickness equation, which basically says that the small deviations in surface height are like the total depth times the convergence. We normally don't write it this way. We have been writing this as divergence of h times u, or something like that. But this, in the same sense that we linearize this by throwing away the advection terms, this is the linearized thickness equation. We threw away the nonlinear product of thickness and u and just take the average depth and the convergence. And this is basically a linearized version of our shallow water equations, which makes it easier for us to think about waves, which are a linear phenomenon, at least at weak amplitudes. Does that make sense? Yeah. Okay.
How are you using guys less than 1 expression?
How are we using that to get these? I guess has it been used yet? It has not been used yet. It will come in the next slide. But we wanted to be sure we're in that limit first. Okay. So here's just the same equations that we just talked our way through. So now let's try and form a wave equation out of these by, let's see, d eta, dy, dt. Here's the d eta, dt. Let's take the d by dy of this equation. which gives us a d by dx dy of u, a d by dx dy of v, taking the average depth to be constant, so flat bottom. So that gives us one part of the story. Hold on. And then we go up here and we say, oh, look, we've got a d by dt of u. So what we actually want to do is we want to cross differentiate in order to take this equation and cancel out the u's. Does that make sense to everybody? So if I take this equation, it's got a u in it, and it's got a v in it, and I want to cancel out this and this by taking the right derivatives of this equation so I can use this term in there. Is that what I've done? Wait, why is that? Hold on. Trivial to solve. Yeah, that's always a dangerous thing. That's usually where there's a big mistake. It's like when you read a paper and it says a trivial calculation can show that. That's where the error is. You gotta go redo that yourself because that's where the mistake always is. All right. Anyway, the a to dy, g over f naught the a to dy. Okay, this is that. This is that. This is something different. G d a to dx f naught. Oh, that's what we're doing. This is where the beta not being small comes in. U equals G d eta dx. What's that balance? Geostrophy. And it's not accurate, right? Because we know that this isn't the real value of f. F varies from place to place. But if we neglect the beta y part in favor of the f naught part, this is a first approximation to geostrophy. So what we've done is we plugged in the first approximation to geostrophy into those two terms, and the first approximation to geostrophy in those two terms. We didn't plug it into this one because f naught is bigger than beta y. So if it was the error in this relationship would be like on a small term anyway. So it's a small term because it has a small coefficient, and then it has a small error. So we can ignore the error and just stick with the leading term. But this one, f naught times v, is much bigger than that one. So we're holding onto the full u and v for that. The same thing is true here. Why can we throw away the other part? Well, because we saw that the Rossby waves were really, really slow, and they were kind of in geostrophic balance. Remember we had that high pressure with the thing that just went around it, and it slowly moved. So we expect the d by dt to be smaller than the Coriolis term. So essentially what we're doing is we're expecting this term and this term to be small, and so replacing them with an approximate version of the velocity isn't going to be a bad error because they're a small term anyway. So we're making a small error in the small terms by being careful to keep track of the big terms and not replacing them with any errors. Does that make sense? So that's what this equation is in this equation. So I've plugged in for the geostrophic velocity in the terms I expect it to be small on this side. But now things are getting simpler because look, u and v only appear in one place now. There are all these crazy eta terms, which is complicated, but here, if I just solve for u and v, I get these kind of crazy equations. So all kinds of crazy derivatives of the sea surface height gives me u. All kinds of crazy derivatives of the sea surface height gives me v. And this is a higher order approximation than this. Does that make sense to everybody? But this term is the first one. Does that make sense? So we're trying to get a correction to geostrophy based on higher derivatives of the sea surface heights through these equations, which we think are true. Okay. So if you put those if I take the x derivative of this one and the y derivative of this one, then I've got a thickness equation, so I can actually write this whole thing together as just an equation in eta, which with some algebra gives you this. d eta dt is the Rossby number squared times ddt of the Laplacian of eta plus the Rossby squared of d eta dx, and I could plug in a plane wave solution to this and get a dispersion relation from that. So let's rewind a little and think about what we did. We took equations of motion on the beta plane. We approximated that the velocities were nearly geostrophic, but not quite. And then we eliminated all the u's and v's from the equations to get a closed equation that was only in etas. And that closed equation in eta, so the sea surface height part, was the thing that gave us the wave equation. So in that sense, to answer Johnny's question, yes, it is a surface wave because the wave equation we got was a wave equation for sea surface height, but it should not be confused with the gravity waves because it's not being restored. We didn't squish it back down with gravity. It's a more complicated set of equations that are the balance for it. I could have done this and gotten the same relation by using the vorticity equation, because what this really is a vorticity equation. This is the sea surface height representing cyclones and anticyclones. So I could have taken those last equations and just formed them into a vorticity equation, and I would have ended up at the same place. So there are multiple ways to get to this, but that's the answer, and then here's the dispersion relation. Okay, so let's look a little bit more at the dispersion, and we also could have done the whole game with reduced gravity and gotten the h of the moving layer and g prime, and it would have given us a slightly different speed, or a different Rossby deformation radius, actually. Okay, so here, if I take that dispersion relation and plot it on our omega k axis, this is what you get. So omega divided by k, what sign is it here? Negative. So the phase speed over here is negative. Omega divided by k over here, what sign is it?
Also negative.
Also negative. Now the omega is positive, but k is negative. So phase speed all the way along is negative. So the Rossby wave propagates to the west, crest and trough, at all wavelengths and all frequencies. d omega dk, the group velocity, is the slope of this line. So if the slope is positive, it propagates eastward. If the slope is negative, it propagates westward. And if the slope is positive, it propagates eastward. So we distinguish these by saying these are the long Rossby waves that propagate westward, and the short Rossby waves that propagate eastward. Does that make sense to everybody? And this is propagation only in the sense of the group velocity, not in the sense of the phase speed. The phase speed is always westward for all of them. But the long waves have both a group velocity and a phase speed that's westward, whereas the short waves have a group velocity that's eastward and a phase speed that's westward. Okay? And you can look at it up here and say, what does it mean to be a short wave? Well, it means that k squared is really big, so this term in the downstairs is important. So the short waves, this term is governing what's going on, and so you could say it even goes inversely with k, and then you can go through take the derivatives and whatever and think about what that means. But for the long waves, k's are small, so it means this term is little, and it's basically beta naught r squared kx with no denominator. So then omega equals minus beta naught r squared kx. And then what's omega over k? Just beta naught r squared. So the long Rossby wave has this relatively simple phase speed, And what's d omega dk? Also beta dot r squared. So the long Rossby wave right here is a non-dispersive wave in that limit. So just like the shallow water equations had a non-dispersive wave limit, so too do the Rossby waves. In the shallow water wave, and then coincidentally, the shallow water waves, it was the long wave limit, and in the beta Rossby wave case, it's also the long wave limit. But these are different because these are still only unidirectional. Okay? I know there's a lot of weird stuff. And that just says the same thing I just said. Okay, so let's think through this figure again. Anybody want to take a crack at explaining how this works? We start off with water at this line, and then we perturb it by pushing it down and up. And what's the thought process then?
Vorticity change.
There's a vorticity change. So if I perturb by pushing poleward, my relative vorticity will respond by becoming anticyclonic. And if I push it equatorward, I will become cyclonic. And so that's what these little spiraling patterns are. And now what's the deal with this dash line versus the solid wave?
The dashed line is how it should, the direction it should move with time.
Yeah, so if you just take the vortices that have to do with this anomaly and it vects that material line with the shape of this, it will head towards the dashed line in the future. So the dashed line is the future location of this solid line Rossby wave. So the solid line, just because of the vorticity anomalies that come with deviations from a latitude line, tend to move towards the dashed line, and the dashed line is west of the solid line. So this particular class of vorticity wave, or Rossby wave, will tend to move westward. And when people were a little confused about whether this was a north-south thing or a stretching and squeezing thing, and you actually can have a Rossby wave that's based on stretching and squeezing when it's over topography, or one that's north-south. And when we are smart enough to put on our potential vorticity hats, we know that those two things are equivalent. It's just, are you adding to F in the numerator or changing the size of H in the denominator? But they're both Rossby waves. They both propagate westward, which is to the left of shallow and over sloping topography, or to the left of north if you're on the planet. Okay, and then we saw the equatorial Kelvin waves too. And we came, so this is the equatorial dispersion relation with all the different waves we talked about on it all at once. Here's the inertial oscillation. Here's the inertial oscillation. Here are different gravity waves. So over here we get omega squared equals gk tanh kh up on these branches. Here is our equatorial Kelvin wave. Here are our equatorial Rossby waves. And then here's the other one that I said we're not going to talk about, the Anai wave, which is a weird other one, which is a blend. It's like a gravity wave when it's high frequency and like a Rossby wave when it's low frequency. It's a blend of the two. So the one piece I haven't explained about this is why am I calling these the equatorial waves? So the Rossby waves don't have to be equatorial, but this particular kind of Kelvin wave does. And remember, the Kelvin wave piece that we talked our way through was what if there's a wall and then we have a decaying sea surface height anomaly away from the wall. Could have equally well said, what if this was the equator and we had a decaying geostrophic anomaly to both sides of the equator? Why does it have to be at the equator and not somewhere else? F has to be opposite sign. So this sea surface height anomaly would tend to push you this way and then get rotated by the Coriolis force into a direction that. But in the southern hemisphere would also be in the same direction. So to have a coherent wave, you would need to be symmetric about the equator, and you'd have to be sitting at the equator to be a Kelvin wave that has a velocity in that direction and zero velocity in this direction. So to make the thing look like a wall, it has to be the equator. It can't be some other latitude line, because then it would have been in the other direction on the other side. Okay? All right. So, and which way do we expect this wave to go? If it was going along the coastline, it would go with the coast on this side, and if it was going the coastline on that hemisphere, it would go with the coast on that side. Which way does this guy go? That way, eastward, because in the northern hemisphere it looks like the coast is on the right, the equator is on the right, and in the southern hemisphere it looks like the equator, which is playing the role of the coast, is on the left. So it's right in both hemispheres to propagate eastward.
So in a place like the Pacific, that'd be going in the opposite direction of the flow of water.
So the wind will be going from east to west, and these waves would be traveling upwind, and they'd be going the opposite direction of the Rossby waves around it. There's a more complicated current structure, which is both this way and that way. So it's easier to remember versus the wind. Okay, we've already talked through all that stuff. All right, we talked about this, so I'm not going to show that again. But let's look at the movie again. So what kind of wave-like eddies are these?
Rossby waves.
Rossby waves, because they're heading to the west, and they're off the equator. We can't really see Kelvin waves, but there could be Kelvin waves running up, zooming along the coast up here. But look at the equator. You can see things that are moving this way, and some things right on the equator that are zipping that way. So we have both Rossby waves, and also this weird Yanai wave, and then Kelvin waves going the other way. So we have an oscillating set of waves going in different directions along the equator. The Rossby wave is a little bit off, and the Kelvin wave is right on the equator. Does that make sense to everybody? Can you see something along those lines? And these aren't really wave-like because they're actually strong, and so all the linearizations we did don't really apply, and that's why they're these little pockets and they're little blobs. They're like waves that are breaking. They're really strong waves, but they are still propagating in the same direction as their wave would, even though they're kind of a breaking wave. Okay. If we look at the current structure, so this is sort of what the currents, we have our big western boundary currents, and we have our equatorial jets, we have our ACC. Those are relatively narrow features, but in the movie, we saw kind of eddies everywhere. So the kinetic energy of time-dependent flow is actually much more uniform over the Earth. It fills in all these regions in between the big currents. So if you went out in the ocean and you measure kinetic energy in the Atlantic, you'd be much more likely to find the eddies, time varying, the waves and the eddies to have much more energy than the mean, unless you were right in the middle of the Gulf Stream, in which case this little narrow jet might win. So in general, in the oceans, the time varying energy exceeds the mean energy. And it's because of all these waves and Rossby waves and Kelvin waves, or their nonlinear eddy component. Unless you're right in the middle of one of these really big currents, in which case they're kind of the same size. All right, I'm not going to talk about the power spectrum. So here's another way of seeing the eddies. This is just like zooming in on that figure. And this is showing sea surface height rather than kinetic energy, even though they're kind of related. And this is the contour, well, these are in centimeters. So those big eddies, so you see the loop current, this current that goes like that, and then later joins up with the Gulf Stream, and it breaks off into eddies every now and then. So these big blobs occasionally break off and then become like a free-floating eddy. And that's a high, so it's an anticyclone. You can kind of see it's wobbling anticyclonic. There goes one. Bloop. And maybe to compare to what you're thinking about the sea surface height variations to do with the Gulf Stream, these are order 25, 30 centimeters high. So an eddy has a sea surface height variation of kind of half a meter, something half, quarter, or half a meter, and which is similar to this, to the Gulf Stream, which is like a meter across it. Where do these guys come from? One place they can come from are the winds. So we just saw those eddies. This is actually the path of Hurricane Katrina. I think we showed this movie the first day. But you can see Hurricane Katrina comes in, and it does an awful lot of mixing to one side, leaving behind a bunch of eddies. So they can come from the wind, or they can come from instabilities of the currents. So the end of the Gulf Stream just kind of wobbles back and forth and sheds eddies all the time, kind of like a leaky faucet. It goes drip, drip, drip. And sometimes they're big blobs, and sometimes there's kind of a narrow stream. So both the hydrodynamic instabilities of the ocean, or external forcing from the winds or tides, things like that, could make these eddies and waves. All right, so any questions on that before we dive into El Nino? Yeah.
So are eddies and waves, eddies and Rossby waves, are those the same thing? Or?
Kind of, sort of. Sort of not. They are both vorticity anomalies and thickness anomalies, and they both would be governed by that original kind of equation, the one we had, except the eddies would be on the nonlinear version of that equation rather than the linear version. So it's like they're large amplitude waves, but the nonlinearity is important enough that they behave systematically different than the waves. So just like the Chelton and Slacks versus Chelton et al. Later paper, they propagate more slowly, and they're drawn to the pole that has the same sign of vorticity that they do. So they have behaviors that the linear waves don't exhibit. Does that make sense? All right. Okay. So we talked an awful lot about this kind of upwelling, where we have a wind along the coast, but we also talked about equatorial upwelling, right? So it goes to the right of the wind in the northern hemisphere and to the left of the wind in the southern hemisphere, so it's upwelling, right? It's diverging at the surface. That's a part of the story. And so we looked for upwelling signatures as being anomalies that were cold water. You see that kind of hockey shaped cold water anomaly, or we could see them because this deeper waters have more nutrients, they bloom in phytoplankton. So you can see the upwelling zones. The upwelling zones are both along the coast, but also along the equator, but in a little bit more variable way. Okay. So we can think about what's going on in the Pacific. So in the Pacific, the winds come from the east to the west, the trade winds. They're also kind of coming inward from the sides, but just let's think about the zonal component of the winds. So what's that going to do? Is that going to make upwelling or downwelling? Upwelling, right? Because it's going to the right of this in the northern hemisphere, to the left of this in the southern. And so, and then there's also going to, if they're going like this, inward, you might have coastal upwelling connected. So that's what we just saw, right? There's kind of a tongue of cold water on this side that's upwelling in the middle of the Pacific and coastal upwelling over here. But, so that's tending to make the water colder at the surface, but then you're also just pushing the water downwind. And so pushing the water downwind is going to tend to make a pressure gradient. Okay, so why am I not talking about geostrophy? Or Ekman?
You're at the equator.
Because I'm at right on the equator. So I'm pushing and there's no Coriolis force right on the equator. So instead, the only thing that can balance the force of the wind would be a pressure gradient that goes back this way. So we would expect the sea surface height to be a little higher on that side than this side, so that there's a surface pressure gradient. And when the sea surface height is higher, what do we expect the picnic line to do? Go deeper, so that the pressure at the bottom, pressure gradients get smaller as you go down. So if the thermocline or picnic line goes deeper, and there's stratification on top of it, making it deeper makes it what? Warmer or colder? Warmer. Okay, so we have wind blowing this way. That's tending to make warm here, cold here, thermocline tilt this way, and also driving upwelling. So all those pieces are linked together on the ocean side. Everybody on board with all that? Okay, now let's think about the atmosphere side. We have warm water on one side, cold water on the other side. What's that going to do to the atmosphere? You have warm water underneath, what do? You get hot and you rise. So you go up, and you probably are also pretty moist because you were just over a warm ocean surface. So as you rise, it's going to rain because as you're expanding, you're cooling off, you can't hold as much moisture, the rain comes out, and in fact, you will heat the remaining air even more as the moisture comes out because of the latent heat release. So this is a very energetic rise of warm, moist air up to about the tropopause, up to the top of the troposphere. And then on this side, over the cold water, you have kind of the opposite effect. Now you're cooling the air, it's coming down and it's closing. So you tend to get a loop with ascent over the warm water, descent over the cold water, and it goes like this. That's called the Walker circulation. This going in this direction. We talked about the Hadley cell, which is ascending and then going that way, but then having a Coriolis force. There's also an overturning just right on the equator that's rising over warm water and sinking over cool, called the Walker circulation. What way is the wind at the surface because of the Walker circulation? In the same direction as the arrows we just drew. Okay, so now which one is the tail and which one is the dog? We just said the winds blow this way and then that makes this happen to the ocean. But I could have equally said the ocean has an SST gradient and therefore the winds go that way. So neither one starts out the effect, they reinforce. So the winds tend to make the ocean SST gradient larger, and the ocean SST gradient tends to make the winds larger. The thermocline tilt tends to affect the Walker circulation. The Walker circulation tends to affect the thermocline tilt. So all these pieces are linked together in a feedback between the atmosphere and the ocean. If I strengthen the tilt of the thermocline and make this sea surface temperature gradient larger, it's going to make the winds larger. And the winds larger would tend to make the thermocline tilt larger. So there's a positive feedback between the two sides. Does everyone understand that? That's the Bjerknes feedback. The Bjerknes feedback is once you have considered this setup along the equator, it will be self-reinforcing because it doesn't matter if you start with the wind and then think about the consequences in the ocean and then end up with the ocean situation reinforcing the wind, or if you start with the thermocline tilt in the ocean and then think about the consequences through the wind back to reinforcing the thermocline tilt, it's self-reinforcing. So if this is the normal situation, if I make the tilt a little steeper, somehow, magically, what do you think is going to happen? It's going to self-reinforce, and it'll tend to stay steeper until something knocks it off. If I make the thermocline tilt a little shallower, it's going to stay shallower. So it's somewhat unstable. It's going to like both the flatter thermocline and the steeper thermocline case as an anomaly away from normal. Or alternatively, the strong Walker circulation, weak Walker circulation case. So what's El Nino? So El Nino is an anomaly in the equatorial Pacific winds, sea surface temperature, thermocline depth, and atmospheric convection. It is exactly that anomaly that's self-reinforcing. El Nino is the one for the flat thermocline case. La Nina is the one for the steep thermocline case. It's the largest climate variability in the world. So it's the thing that changes the sea surface temperature more than any other variation, except for the seasonal cycle. So it's the largest unforced, like natural variability. And it's typified by, so this is the El Nino side, the warm eastern Pacific temperature. So the cold tongue gets warmer. Weakened easterly winds, cold tongue gets warmer, that makes the SST gradient weaker, makes the winds weaker, weakens the Walker saw. Flatter than normal thermocline tilt, which is consistent with the warm eastern Pacific SSTs. Deeper than normal thermocline, that one's not so obvious, but we'll talk about that one in a minute. Atmospheric convection and precipitation anomalies centered on top of the center of the warm water, which goes a little bit closer to the east because it's warmer than normal in the east. And then recurs every 3 to 7, maybe 2 to 7 years. Okay, so let's look at what one looks like. This is sea surface height in the bumpiness and sea surface temperature in the colors. So this is a peak El Nino. This is the November of 1997, which is one of the bigger ones. It's happened in this, whatever, the 20th, it is the biggest one of the 20th century. I guess I can say that. It's not, maybe or maybe not the biggest one since the 80s, because there was a big one in 2016, 15, which might be a little bigger. So, sea surface height is anomalously high. Why is that? Sorry, these are anomalies, not the actual temperature. Why is the sea surface high? If we go back to this, why is the sea surface high going to be high if it's the thermocline is flatter, the winds are weaker? Yeah, because we had talked that there needed to be a pressure gradient to balance that wind stress, but if the winds got weaker, it's going to relax. So we get a sea surface high, and if we shut down the upwelling, it's going to get warmer. And so that's the sea surface height, and that's the warming that goes with the decreased upwelling. Okay? So does anybody know why it's called El Nino? Other than something else? Yeah, exactly. So it tends to peak around December of each year. And since December is near Christmas time, which is when the baby Jesus was born, the fishermen who discovered it named it after baby Jesus, or El Nino, because they said it comes at the same time as Christmas. Here it is. So it's called that. And then it's called La Nina. Does anybody know why it's called La Nina? Because George Philander, this guy at Princeton, was very clever, and he thought it'd be funny to flip the gender and call the opposite sign the opposite gender. That was why. So anyway, so if you plot the anomaly temperature in a certain region, which is kind of that eastern Pacific side, this is what it looks like for a bunch of different El Nino events. It goes up something like 1 degree to 2, maybe 3-ish degrees, and it peaks between November and January, sometime in December, on the years that are El Nino years. A normal year would also have a seasonal cycle, but it wouldn't go as high. Okay, so this is what the El Nino case looks like. It's that same image. We remove the cold tongue. The anomaly winds are going backwards, but the winds might just be kind of low, close to zero, with the convection centered on top of the now Pacific-wide warm water rather than all the way over here on the west side. The thermocline relatively flat and also relatively deep, and that's the situation. The La Nina case, the thermocline is really steep. The convection is way over on that side. The winds are really strong, and the Walker cell is really strong. Does that make sense? And in both cases, or all three cases, the Bjerknes feedback is part of the situation. And when you tend to tilt the thermocline, you tend to tilt it more. So once you get stuck in one of these anomalies, it looks like it's going to stay there. So we'll actually see that there's something that will kick it out, and that'll have to do with how we get the 3 to 7 years. As you get stuck in one, and then something will happen that kicks you out. And here are all three side by side, just so you can see. So the cold tongue and the warm pool are either a warm pool expands to the east, or the cold tongue expands to the west. Convection moves around. The thermocline goes up and down. The wind leads to tilt. The tilt leads to the wind. All these pieces are all together. Does that make sense to everybody? That's the essence of a lot of El Nino. All right, are there any questions about this before we move on to now the wave-like part? So this is sort of like the equilibrium theory of the tides. Now we're going to think about the dynamic theory. What are the waves doing that support this sloshing back and forth part? No questions. All right. Here's a not schematic version of what it looks like. This is the SST anomaly in December of 1991. So is that an El Nino or a La Nina? This is the anomaly SST. It's an El Nino because it's warm. And then this is now the power spectrum. And sorry, it's backwards in the way we usually see power spectrum. This is power spectrum with period down here. But this hump right here, or this set of humps, are the statistics of El Nino over the observation window in this. So somewhere in between 2 and 6 years is where the power sits. That's where the wobbles are. And it tends to, this is the autocorrelation, this is kind of hard, but which flips sign about every 24 months. So it's going from positive to negative to positive to negative every 24 months. And it's peaking in November, December, January, as in terms of where the most variability is. And then here is 1988, a nice big La Nina, which looks like an enhanced cold tongue. And these off-equatorial patterns are actually also part of the larger system when you think about the way that the winds in different parts of the ocean get connected together. So this is the composite of all of the variability in the Pacific from 1950 to 2000. And you can see that it looks an awful lot like El Nino or La Nina. So all this other stuff doesn't vary too much. The variation is totally dominated by that signal. Does that make sense? So this is really, well, I should say this is the SST anomaly after you remove the seasonal cycle. This is the other than seasonal SST variability. So that's the sense in which this is the most important mode of sea surface temperature variability in the Pacific. If I had zoomed out and done the same thing in the whole world, this still would have showed up as one of the biggest regions of SST variability. So this is a really, really big oscillation. All right.
Question.
Mm-hmm.
Why does it only appear at the east of Pacific but not on the west?
Yeah, so that's interesting. Why doesn't the warm pool get warmer? Not just the cold tongue get warmer and colder, but why does the warm pool stay put? The warm pool is actually pretty tightly connected through radiation to be fixed at the temperature it's at. It can't heat up much and it can't cool off much. So it's more locked down by the incoming sun and the outgoing radiation lost back to space the maximum temperature that it can take before it starts convecting. So that temperature of that part of the world is kind of locked to be at the 27-ish degrees, like as hot as the ocean water can get before it starts raining and makes itself cooler, or before it starts losing radiation back to space. So this side is the side that tends to vary. To put it another way, the coastal upwelling and the equatorial upwelling are having a bigger signature on the temperature over here because the thermocline is closer to the surface. So when you change the upwelling, you're actually contacting colder water just underneath. So as the winds vary, this side varies in temperature more. This side, the temperature surfaces are pretty deep, regardless of even in an El Nino, they're still pretty deep. So they're not really you're not seeing the cold water below because the thermocline is deeper on that side. So you're pretty much raising and lowering the mixed layer on that side, but on this side you actually are bringing up the thermocline close enough to the surface to appreciably change the SST. Okay. So one thing that you'll see if you read any El Nino boxes, if you decide to write your paper number 4 in El Nino, which you certainly can, is people will talk about the Nino indices. And the Nino indices are the average of some variable, like wind or temperature or salinity or velocity, in one of these 6.5 boxes. There are 1, 2, 3, 4, 5, and 6. And then they added this other one that they call 3.4, which is half of 3 and half of 4. Why they call it 3.4, it's kind of like 3 plus 4 over 2, or maybe 3.5 or something. But anyway, they decided to call it 3.4 because some of the El Ninos are very strongly centered in the middle of the Pacific. Some are more to the east. So comparing the statistics of Nino 3 versus Nino 3.4 is sometimes interesting. But there's a long history of people making crazy things. But anyway, the idea is, so why do you think boxes 1 and 2 are important? They'll measure the coastal upwelling. 3 will be kind of, or 3.4 will be kind of the center of the El Nino or La Nina SST action. 4 could be the center of the convection. So seeing the variability in the convection. The winds over box 3 would also be interesting. 5 and 6 are actually triggering events that tend to send waves into that region that get reinforced. So if I had an anomaly in convection in 5, or an anomaly in winds in 6, it might trigger a wave-like response that would kick something off. And actually, the other thing that 5 is good for is, in a strong La Nina, 5 gets a lot of rain. So I don't think I have a picture of Queensland. What year was that? 2012? There was huge amounts of flooding in northeast Australia during the last La Nina, like unbelievable flooding. And it's because basically the warm pool just relocated itself so that all that convection just sat on Australia for like months. And it just rained and rained and rained and rained. So that is a strong La Nina tends to have that effect, whereas a strong El Nino, the convection comes over here and actually can frequently cause drought conditions in Australia and Indonesia. Okay. The other thing people say about El Nino sometimes is they'll call it ENSO, which is a conjunction of El Nino and the southern oscillation. So El Nino and La Nina are the phases of that, but ENSO, the El Nino southern oscillation, is the joint pattern of the winds and the SST variability. So sometimes people say the SST is what defines El Nino or La Nina, but then the winds are more like the southern oscillation, which is a wind and air pressure anomaly strongly oriented. So let me show you. So if I take the Nino 3.4 index, which is the SST in that 3.4 box, it gets warmer sometimes, colder, warmer, colder. So what's the warmer one? And the colder one is La Nina. If you look at the Southern Oscillation Index, which is the air pressure difference between Darwin and Tahiti, So if there's high pressure at Tahiti and low pressure at Darwin, which way did the winds go? From Tahiti to Darwin and vice versa. So even before they knew that these oscillations were occurring, they knew that there were sometimes wobbles in the air pressure difference between those two weather sites. And you can see that when you have a negative in that pressure gradient, you tend to have an El Nino. So the negative signal here is weaker than normal winds on this side of the Pacific. And the positive here is stronger, which tends to be aligned with La Nina. So the wind, the atmospheric pressure variability, which is related to the winds, varies together. So when you put all this together, sometimes people call it ENSO. So the combination of the atmospheric variations and the oceanic variations. That's what Bjerknes looks like. This is the younger Bjerknes, yeah.
So you said the pressure oscillates high and low.
Mm-hmm.
Is that what's called a dipole?
Yeah, it could be. If you saw this pattern, you might call that a dipole of atmospheric pressure. Dipole is used very loosely in atmosphere and ocean sciences. And what dipole means in particle physics is much more precise than that. But if there's two blobs of opposite sign, people will call them a dipole. Okay. So this is Bjerknes the younger. His father was also a meteorologist. But anyway, this is the Bjerknes that came up with this idea of the Bjerknes feedback, which is this self-reinforcing stuff we already talked about. Oh. Okay. So we talked mostly about the thermocline tilt, but there's also Ekman transport related to that upwelling. And in fact, because the winds farther off the equator are not wobbling, the wind stress curl is changing as you're changing the winds at the equator. And if the wind stress curl changes, what does the sphere drop relation tell us? Upwelling and downwelling and gyres, or meridional transport, right? We go poleward when we have downwelling curl, driving curl, and equatorward when you have upwelling. So as that curl is going up and down, it's driving sphere drop water in and out of the equator. So the equator is kind of breathing during the El Ninos and La Ninas. So there's a flushing of water associated in the meridional direction associated with this. So, okay. And in the sense of during an El Nino, the winds weaken, so the Ekman upwelling is less, but the sphere drop actually gets stronger, so you tend to flush hot water out of the equator during El Ninos, and you tend to flush it less during La Ninas. So you're moving warm water in and out of the equator in phase with the El Ninos. And frequently, actually, I just saw a paper that came out in Nature like last week that said that that's the primary variability in the ocean heat transport in the world. That's the biggest variability in the pole to equator transport in the oceans. So anyway, maybe it's not, but whatever. That's an interesting way to quantify it. Okay, so now let's think about the dynamic theory. So we've got this crazy zoo of waves. So El Nino is slow, 2 to 7 years. So how do I find slow on this figure? Over C. No, sorry. It's omega, that's the part. So it's C, sorry. This is weirdly normalized. C here is just a constant, just GH. So slow in terms of low frequency is just close to this axis. So close to this axis, so if this is the 1 over the pendulum day, except for in those weird units, that's the inertial oscillation. So these are strongly sub-inertial waves. So 2 to 7 years is like 700 times slower than the inertial oscillation, so it's going to be right down here near the origin. So we're pretty much just going to see which two waves are in there. The Rossby waves, in particular the long Rossby waves, and what else? Kelvin, this guy. So on those periods, we're going to see Rossby and Kelvin waves sloshing around. And in fact, that's what we see. So if we have a wind anomaly, we try and kick that Walker circulation, give it a little boost. We get Kelvin waves that shoot out to the east and Rossby waves that shoot out to the west. And so here is what it looks like in a model, an idealized model. If you make a kick burst of wind, after 25 days, you see this double-peaked Rossby wave going that way, a single-peaked Kelvin wave going this way. After 50 days, the Kelvin wave travels faster than the Rossby wave. It actually makes it to the side. It starts to spread out, going with the coast on its left in the southern hemisphere and the coast on its right in the northern hemisphere. And then it continues, and it continues more. But the Rossby wave actually gets all the way to the wall and reflects and starts turning into a Kelvin wave, heading back in the middle, this little blue tongue running eastward. And the original Kelvin wave is now reflecting backwards as a Rossby wave. So this Kelvin wave goes, hits the wall, spreads up along the coast, and starts coming back as a Rossby wave. And this sign is such that this is, if blue is downwelling and red is upwelling, so that, suppose that was a burst of wind and eastward wind, which would have made a little bit of sea surface height anomaly on this side and sea surface low, you can keep track that downwelling Rossby wave propagates away and then returns as a downwelling Kelvin wave. The upwelling Rossby Kelvin wave goes, reflects off the wall, and returns as an upwelling Rossby wave. So that this phase, which you might say was the peak of the El Nino, because the sea surface high, the upwelling Kelvin wave has reached this side where the Bjerknes feedback would kick in, is extinguished by a downwelling Kelvin wave in this model about 275 days later. Okay. So what that means is a westerly wind burst can cause these waves. Eventually they'll kick in to the Bjerknes feedback and make an El Nino, but the waves reflect off the walls and sometime later will actually send an extinguishing wave back to kick you out of the El Nino and back into a neutral or La Nina state. So what sets the 2 to 7 year wobbles has to do with all these waves ringing around in the basin. And the way that you trigger an El Nino, you might trigger it remotely by kicking off those waves in some other part of the Pacific, and then when they zoom around and end up in the El Nino zone, then the Bjerknes feedback will set in and they'll reinforce. Okay? So this is a nice way to see it. This is from a paper by Antonetta Capitandi. And so she takes a model and she takes a transect just north of the equator, down like this, and then back, and unwraps it. And then this is sea surface height, yeah. So this is section 1, starting from here, going to there. This is section 2, going from here to here. And this is section 3, going from here to here. And that is increasing time. So it's a Hofmuller diagram. So there's a sea surface high anomaly that goes up, 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 which means it's going from point 1 towards point 2. Then it hits the wall and shoots along the wall, going south. Then it turns into a Kelvin wave and shoots along that way. So the Rossby wave has a reflection stage and then a Kelvin wave. So they're all linked to each other. And you can see that at least in this model, it's going, is this actually a model? Or is this data? This might even be data. I don't know, actually. I think this is data. So here you're seeing, so these are Rossby waves turning into reflecting, turning into Kelvin waves. And when they get over here and get really deep and dark is when you've triggered an El Nino or a La Nina, depending on the sign. So if we watch a movie, this is the wind stress, this is the sea surface height, this is the SST. You can see there goes a beautiful Kelvin wave. It's spreading out, warming up. There's a big El Nino. So let's watch it again. There's a Kelvin wave shooting along, makes its way to the eastern side, at which point the sea surface height goes up and the temperature goes up, making an El Nino. The winds are crazy. There's all kinds of other stuff happening. But you might be tempted to say that that wave got kicked off by a wind burst. But it's very hard because there's so much variability in the wind to figure out exactly which burst it was. But that kind of variability in the wind and then waves propagating out of it is how we essentially predict this kind of phenomenon. Okay, so this is the same kind of schematic as we saw before, except now the thermocline tilt anomaly is being emphasized, and they're also pointing out the sphere drift flushing part of it. So if you're in an El Nino, which means, sorry, this is an anomaly tilt, which is like the hardest thing to think about. This is flatter than normal, even though, or it's tilted backwards, I don't know, whatever. Flatter than normal conditions. The sphere drift transport, because the winds are very weak on the equator, is away from the equator. So not only do you have an anomaly in tilt, but later you're going to find that the thermocline is shallower. And then when the thermocline is shallower, you're actually going to be more sensitive to the winds. And so you're likely to end up in a La Nina state, which now this anomaly sphere drift transport is inward, which gives you a deep anomaly. So a different model of how El Nino works is this, which is called the recharge-discharge oscillator, where you charge up during a La Nina with upper ocean water, and then you discharge during El Nino. And so you go back and forth between El Nino and La Nina and adding more surface water and taking it away. And a different way to put that is, if this is the Nino 3 index and this is the depth of the thermocline, the data tends to go, where's it? Where's the beginning? The beginning is here. Okay, the beginning is here. So it goes zoom like this, around and around and around that way, which means that an El Nino precedes a discharge, because it's going this way, and a La Nina, this side, precedes a recharge. And so you're going around and around in the same cycle with the Nino 3 index and the thermocline depth out of phase with each other, but you tend to go around in the same direction. So you could predict an El Nino by saying, hey, I'm really recharged right now. My thermocline is really, really deep. I expect to see an El Nino soon. Or you could say, I'm in an El Nino right now. I expect to have a shallow thermocline soon. Or if you took the average period of this, you could say I'd be switching from an El Nino to a La Nina in that amount of time. Does that make sense? Okay, and so how do we get figures like this? Well, actually, this is such a big phenomenon that the people of the world have decided that it is worth putting out this mooring array. So these are permanent moorings all over the world oceans from 10, well, actually even 15 north to 15 south. So each one of these has like 6 kilometers of anchor line on it. And some of them, the blue ones, have a weather station on the surface, and the red ones are subsurface moorings, but they can go retrieve the data acoustically. And this monitors the evolution of the salinity, temperature, and thermocline tilt. And actually some of them have current meters on them too, all the time, because this data is how you locate yourself on this figure in advance, and you know that you're due for a discharge, which means an El Nino is coming. And there's a similar kind of phenomenon, which we didn't talk about, in the Atlantic. It tends to be shorter, like every season, and there are other weird phenomena that are not like this in the Indian as well. So, but, I mean, that's like, each one of these probably costs $2 or $3 million. I mean, this is like an unbelievable investment. It has to be replaced every couple of years because they wear out. So, like, this is just like, and then every single time you have to take a ship out just to service that mooring. I mean, this is like, if it didn't cost billions and billions of dollars in damage, or potentially save you billions and billions of dollars by being able to plant your crops accordingly at the time of year, this would not be worth it. And actually, some people think it's even not worth it because some of this data is redundant with what you can see from satellites. But of course, you can't see the thermocline depth from satellites. You can only see the sea surface height, the SST part of this story. So, but here's what that data looks like. If you look at it in El Nino, so this is the 1997-98 one, there's the Kelvin wave propagating now on the thermocline depth anomaly. And then after it gets over there, then it starts to warm up at the surface, and you see the sea surface height. So knowing that that thermocline depth anomaly was lurking in the Western Pacific and about to shoot across as a Kelvin wave, and now here comes the La Nina sneaking in the following year. Also, more easily visualized as an anomaly in the thermocline depth than it was in all the noisy stuff at the surface. It's got other things on it. So that array helps us predict by looking for this kind of cleaner signature of the El Ninos and La Ninas by looking for the Kelvin wave on the thermocline depth, or the thermocline temperature, I guess. Either way, whatever. As it's going up and down, it's changing the depth. They're all a little different. This is like in the 97-98 one we've seen a bunch of times to see the Kelvin waves come by, and there it's deepening. And then this is the 2015-2016 one, which is another big one. But you can see this one's kind of more in the middle. That one's more in the east. And once they're up and set up, you can see them pretty clearly. But it's not obvious that they get followed by a La Nina in the same. See, that one got followed by a La Nina. This one is not really. Each one has kind of different wobbles. It's not just a clean oscillation. It's like a lot of superimposed weather and internal variability on top of the El Nino. So you might have guessed that that first Kelvin wave over there was going to set up into something, but it doesn't. It got there too early. It wasn't in December. It got there in like October. So you had to wait for the next Kelvin wave to come in that then hit it at the right moment to amplify in the season it likes to. And then this one breaks up. That one's still kind of lingering. But then that one actually grows the La Nina stronger than this one does. So they're different. Okay, we don't have too much time. Let me wrap up. So these guys, Mark Kane and Steve Zebiak, made the first successful forecast model, dynamical forecast model of this. And it's pretty much just an upper ocean with an atmosphere that converges and diverges and makes a Walker cell on top of it. It's a very simple thing. You can run it easily on a laptop. Or you probably have a phone for like millions of years now. This is what you get. So this is what the ENSO time series looks like. This is 82 back here. That's the big 82-83 one. Here's the 97-98, 2015, 2016. But you can see it's really kind of wobbly and weird. It's not everyone is the same size, and they definitely don't oscillate, obviously. Right now, we're predicted to go into a modest El Nino next winter. This is the, what do they call it? The cone of predictions. So these are all these different ones are different models made by different modeling institutes, and they're all predicting, and this is where we are observed to be, right there and there. And so some of them, like this one from King Abdul University of Science and Technology in Saudi Arabia, is saying we're going to get a really strong one. And this model, which looks like it's syntax. Oh, that's a Chinese model. It's saying that we might switch to a weak La Nina or neutral conditions. That's kind of the spread. This is the average of all of them, which says we're going to pretty much stay where we are. And then there's other forecasts and dynamical averages and other things that are going on. But basically, our prediction from now is that we're going to stay in a pretty weak, like 1 degree El Nino through the next year. They stop here because if you just extend this out, then they just get wider and wider, and then they would go all the whole range from plus to minus, and so there's no predictions. We can predict about this far out. We can't predict another year out. That it becomes too wobbly and chaotic by then. Once you've got an El Nino, it changes the weather throughout the whole world. This is such a big oscillation, so this is just a map of different things. So right underneath the Walker circulation, you'd expect it to be wet, where the convection is stronger, and dry, where the convection has moved away from. But even over here, where we are, we tend to get warm years during an El Nino year. And down here, South America, you get wet rain. On the other side of the Indian Ocean in southern Africa, you tend to get dry and warm conditions. So this is like a huge change. Actually, the length of the day gets longer, detectably longer, because the sea surface height, so much mass comes up on this side of the ocean from below that you actually slow down the Earth by, like an ice skater, sticking the leg out. You've changed the moment of inertia of the Earth. It's a huge effect. Okay, and the last thing I want to say is people try in paleoclimate to reconstruct this. This is Peter Molnar, who's one of the people who's done a lot of thinking about this, and you can try and figure out whether the east-west tilt changed looking back in the past based on critters that like to live in warm water and critters that don't. Doesn't matter too much, but one of the most important and complicated parts about this story is it's not clear whether you're seeing changes in the mean tilt of the thermocline or the amount of El Ninos. Like maybe you're just getting more El Ninos rather than fewer La Ninas, or maybe they're getting bigger or smaller, and you can't wrap that up because this is millions of years in the past, and that's all the data we have. So it's like 1 point every 200,000 years, which isn't quite resolving El Nino and La Nina. So there's a lot of paleoclimate work trying to get higher frequency, better resolution of this to see whether the variability is changing in the past, not just the means. Okay, that's enough. We can stop. Are there any more questions? So that's El Nino and La Nina, which if you wanted to would be a fun thing to write paper number 4 on. As a wave phenomenon, a cool thing to do would be to try and find that Capitundi 3 transect Hofmuller diagram in echo. That would be a very cool thing to do. And there is a really big La Nina in 2011, 2012, and there's a really big, also a pretty big El Nino year in the span of the echo years. So you can go through and see a bunch of big events if you wanted to look for that. It's kind of a cool way to think about what that data's got in it. All right. Cool.
Can I ask a question?
Oh yeah, questions about the paper while we're pinning down.
So